So, come back to this linear algebra course. In the last lecture I have defined the permutations, and we have been seeing the permutation group. We are studying the group Sx permutation group. Group on the set X, and we will assume this X is a finite set. And what we have seen is, let me summarize what we have seen so far. We have seen that this Sx group under composition, this is not commutative group, not commutative. Also we know the cardinality of order of this group, that is cardinality of Sx is n factorial, where n is the cardinality of x. We have also seen that this group does not depend on x, but it depends only on the cardinality x. That means if x and x prime are two sets with the same cardinality, that means there is a bijective map f from x to x prime, then this map f induces an isomorphism from Sx to Sx prime. This is I have denoted by kappa f. That means any sigma goes to f inverse sigma f. This is a map from x prime to x prime, and if sigma is bijective, this is also bijective, so that means it is indeed an element here, and this kappa map is a group homomorphism. So, it is a group isomorphism. So, to study this group permutation group, we can without loss we can assume that X is our standard set which has n elements, that is this 1 to n set. And in this case I will denote S of 1 to n by shorter notation S suffix n, and this is called permutation group on n symbols. On n letters or n symbols, and we want to study this group. And in the last time I have motivated you that if one wants to study finite group theory, it is enough to study this group in a very detailed way. So, if you have a good knowledge of the permutation groups, then you will get a knowledge about arbitrary finite group, because any arbitrary finite group is a subgroup of this Sn for some n. That was Cayley's theorem, right. And also we have noted that the center of this group is trivial. Center of Sn is only identity. Center means all those elements sigma in Sn, all those permutations which commute with every other permutation, sigma tau equal to tau sigma for all tau in Sn. This is the center of, this is called the center of Sn. This is clearly a subgroup, is a subgroup of Sn. In general, if you have a group G, then the center is set of all those elements of G which commute with every other element of G. This is a subgroup of G, and it is the equality G equal to Zg if and only if G is abelian. So, in some sense it measures the commutativity of a group. In general, this is a subgroup. If it is equality, that is equivalent to saying G is abelian. Abelian means any two elements commute. Now, in the next few minutes we are going to study some elements of this group Sn, namely the cycles. Cycles are special permutations. So, what is a cycle? So, it is a k cycle, where k is in between, k is from 1 to n. So, k cycle means a special permutation. So, that means this is usually denoted by this notation I1, I2, Ik, where you fix elements I1 to In, I1 to Ik in between 1 to n, and this permutation means it whatever the letters are mentioned here, only they move under this one. Let us call this as rho. That means think of rho as a permutation which maps first of all any j to j, where j is different from any one of these, where j is not in this subset, I1 to Ik. So, all the j's outside these are fixed, and sigma of I1 is I2, the next one. Sigma rho of I2 is I3, and so on. Rho of Ik minus 1 is Ik. So, this goes under this, under rho up to here, and the last one goes back to the first one, and rho of Ik is I1. This is clearly a bijective map and it is a permutation. This permutation is called a cycle, k cycle. And why is it called k cycle? You can also diagram wise you can write it. So, I1 is here, I1 goes to I2, this is I2, I2 goes to I3, this is I3, this is rho, and keep doing like that. Ik minus 1 is mapped to Ik, and Ik is mapped back to I0. So, it looks like a cycle. That is why it is called a k cycle, and k because the number of elements which are moving is k. So, for example, 1 2. 1 2 is a cycle which maps 1 to 2 and 2 back to 1. This is cycle of length 2. If you have 1 2 3, then you have 1 2 3. So, 1 goes to 2, 2 goes to 3, and 3 goes to 1. So, it is a 3 cycle and so on. So, these are very important in the description of arbitrary permutation. So, for example, I want to introduce now notation. Given arbitrary permutation sigma in Sn, I want to call the elements, all those elements I in 1 to n which do not move by sigma, that is sigma of I is I. These are fixed points of sigma. So, as a map it does not do anything to them, it keeps them to themselves. So, the real sigma can be understood outside this set what happens. So, the support of sigma is by definition complement of these fixed points of sigma in 1 to n. So, n star n minus fixed points. This is called the support of sigma. And these are called fixed points of sigma, and their union is obviously support sigma union fixed points. This first of all the disjoint union because nobody is in common, and this you get the whole thing. So, to understand a permutation, one has to understand its support. So, for example, if I write sigma as a cycle, let us say 1, 2, 3, and say this is a permutation on n letters, where n could be say 10. This means we are only seeing 1, 2, 3. That means other than 1, 2, 3, every element is fixed. So, obviously fixed points of sigma is which are not listed here and up to n. No? So, that is 4, 5, 6, 7, 8, 9, 10. These are all fixed points. They are unnecessary they are not shown up in a notation because it is unnecessary burden on the notation to say them. And these are the support is the remaining one. So, support is seen to be 1, 2, 3. So, or for example, you may write I comma j, this is sigma, then obviously the support is only 2. Support has only 2 elements, I and j, and the letters which do not appear here, they are fixed. That is why they are called fixed points. Also, the 2 cycles are called transpositions. Okay, and now our problem is to write every permutation as a product of cycles, and not only arbitrary cycles, but the disjoint cycles. So, first let us recall a definition. If I have 2 cycles, sigma and tau, one is a k cycle and the other is a L cycle, we call them disjoint sigma, or this definition works for any permutation. So, I write only for cycles. Take arbitrary permutations, then we say that sigma and tau are disjoint if their supports are disjoint. Support sigma intersection support tau is empty. Then we call the permutation to be disjoint. For example, if I take a permutation n equal to 10, and suppose I take 2 cycles 1, 2, and the other is 3 cycle 3, 4, 5. This is sigma, this is tau. Then the support here is 1, 2, support here is 3, 4, 5. They do not have anything in common, therefore sigma and tau are disjoint. And the advantage of disjointness is, if sigma and tau are disjoint cycles or disjoint permutations, then they commute. Then sigma tau equal to tau sigma, and this is obvious because the elements which are moved by tau, they are not moved by sigma, and elements which are moved by sigma, they are not moved by tau. So, this equality is obvious. So, this is because tau of any element I is tau if I is in the support of sigma. I is in the support of sigma, so it cannot be in the support of tau, therefore tau I has to be I. And similarly, sigma j equal to j if j is not in the support of tau. J is in the not in the support. If j in the support of tau, j in the support of tau, that means j is moved by sigma, then j cannot be moved by sigma, therefore it is fixed. So, now we want to decompose. So, the main problem is problem is to decompose sigma into disjoint cycles. What does that mean? That is, in the notation, I want to write sigma as sigma 1 product sigma r, where sigma 1 to sigma r are cycles and are disjoint cycles, and they are disjoint. They are pairwise disjoint. That means for any I and j in between 1 and r, I not equal to j, support of sigma I and support of sigma j, they are empty. Or in other words, this support sigma I, this union is disjoint. I is from 1 to n, I is from 1 to r. This is a partition of the set support sigma. And because they are disjoint, I can reorder also them, that the product will not change. And this is very easy. So I have to give you a partition of the set. So this is very easy. So only thing we have given is a sigma. Sigma is a permutation given. Now the sigma defines equivalence relation. Define relation. I will denote tilde sigma on the set 1 to n by what definition? I is related to tilde sigma j if j equal to sigma power m of I for some m in integers. Remember, when I write a negative integer, sigma minus inverse is, sigma minus 1 is, for example, the inverse map of sigma. Inverse map of sigma. Sigma is a bijective map, so inverse makes sense. So sigma inverse is that, and sigma minus power any L is by definition sigma inverse power L. So where L is a natural number. So that we define all powers of sigma, all integer powers of sigma are defined. And this, now let us check that this is an equivalence relation. So what do we have to check? We have to check three things: reflexive, symmetric, and transitive. So reflexive, to check reflexivity, you have to check I is related to I, but well, I will take m equal to 1. So in this case, take m equal to 1. Symmetric means if j is sigma power mi, then I will be equal to sigma power minus mi. If I equal to sigma power mj, j equal to sigma power mi, then I will be equal to sigma power minus mj. Just apply sigma power minus m on both sides, and then you get sigma power minus m. Sigma power m times sigma power minus m is identity maps of this. Transitivity, if I is related to j under sigma and j is related to k under sigma, this means j equal to sigma m I, and this means k equal to sigma l j. Then you apply sigma l to this equation, you will get sigma l j, which is sigma l of sigma m I, which is sigma l plus m of I. On the other hand, this is k. So k equal to this. So that shows that I is related to k. So we have checked that this is an equivalence relation on the set 1 to n. So the equivalence classes are subsets and the equivalence classes will form a partition. So, this relation will give a partition of the set n star n. So, in this partition some element could be singleton, some element may not be singleton. So, in this we have written this as I1 disjoint I2 disjoint IR, and the remaining ones I will still write IR plus 1 union IR plus S, where IR plus 1 is singleton. This IR plus 1, I do not need to write what it is, IR plus 2, IR plus S are singletons. And the I1, I2, IR will have cardinality, all Ij will have cardinality bigger equal to 2 for j equal to 1 to r. And each one of them, I1 will correspond to sigma 1. Sigma 1 will be the cycle. What cycle? Now you start with any element of I1, I, then apply sigma to that, that is sigma of I, then sigma square of I, and so on, and then there will be a time where you will have to come back to I. So, that is sigma power k1 minus 1 I, and then you get back to I, because for every so when you want to check this, you start writing distinct ones, and the first time it is not distinct, it has to go back here. That is very easy to check. I will leave it for you to check that. So, I2 will give, so this I1 will give, and all elements of I1 are exhausted. So, I1 will give K1 cycle, where K1 is the cardinality of I1. So, I2 will give sigma 2, which will be K2 cycle, same argument. So, where K2 is cardinality of I2, and so on. IR will give sigma R, which will be KR cycle. And note that because these I1, I2, IR are different, these are commutative. These sigmas will commute with each other, since I1 to IR are disjoint, are pairwise disjoint. This permutation, these cycles K1 to KR, sigma 1 to sigma R are pairwise commutative, because support of sigma j is precisely Ij. Because of this, the supports do not intersect, therefore those cycles will commute. So, therefore, we only have to check this equality, sigma equal to sigma 1 to sigma R. Okay, to check this equality, remember we have decomposed this set into a disjoint union I1, I2, IR, and the remaining guys are singletons. These are singleton means, that means sigma of them, So when I apply sigma, so for example, if I want to call this element as B1, then sigma of B1 has to be B1, because that is the equivalence class of B1. Similarly, all these guys are fixed under sigma. And these are the only elements of equivalence class. That means sigma, if you apply both sides, they are equal here. Sigma of B1 is B1, on this side also is B1. Therefore, all elements of IR plus 1 union this R plus S are fixed under sigma. So they are also fixed under this, and also under each sigma 1 to sigma R. So when I evaluate this side on an element from this set, it is fixed that it is itself, and here also it is fixed. Therefore, the equality happens on this set. And the remaining set, now I only have to check that sigma restricted to Ij is same as sigma restricted to J for every J1 to R. But that is also clear, because sigma restricted to Ij, this right hand side, only sigma J is moving, and the other cycles they are keeping it fixed. So therefore this equality. So we have proved that every permutation we can write it as a product of disjoint cycles. So every permutation is a product of disjoint cycles. Let me give some small numerical examples so that you feel happy. Okay, some small example, let us write it. What is the procedure? We will write the recipe. So sigma is the permutation on 10 letters. I am doing it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1 goes to 4, 2 goes to 6, 3 goes to 8, 4 goes to 10, 5 goes to 1, 6 goes to 3, 7 goes to 5, 8 goes to 2, then goes to 9 goes to 7. Who is remaining now? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is clearly a permutation, because as you would have noted that I check that the next row is all distinct elements of from 1 to n. Now what is our recipe? Our recipe is start with 1 and look at its image under sigma, that is 4, write it 4. Look at 4, where does it go under sigma? 10. So write the next element 10. Look at 10, it goes to 9. 9 goes to 7. 7 goes to 5. 5 goes to 1. Goes back to 1. So complete it. Now look at who is left in this. 2 is not appearing here. So start with 2. 2 goes to 6. 6 goes to 3. 3 goes to 8. And 8 goes to 2 back. So therefore sigma is a product of these two cycles. These are cycles. This is 1, 2, 3, 4, 5. This is a 6 cycle. No, this is 5 cycle. And this is 3 cycle. Now is it correct our convention is 5 or 6? No, this is 6 cycle. That is our convention. This is 4 cycle. Remember the 1, 2 is a 2 cycle. the number of elements in that cycle is a 2 cycle. Number of elements, if it is 1, 2, 3, number of element is 3, so it is a 3 cycle. Okay. So, now the next thing I want to discuss is how do you compute the orders. Okay. Next, when we come back after the break, we will explain how do you compute the order of a cycle, and therefore, once you compute order of a cycle, we will be able to compute order of an arbitrary permutation. So, we will come back after the break.